All right, so we're going to start off with 11.2, arcs and chords. A central angle is an angle whose vertex is the center of a circle. Remember that theta is the name that we're going to use for an unknown angle. And an arc is an unbroken part of a circle consisting of 2 points called the endpoints and all the points on the circle between them. So in our little diagram here, the arc is the red piece, and then you can see at theta, that's the center of the circle. So that angle, theta, whatever that angle is, whether it be 50 or 40 or 60, that will be the measure of the arc. All right, so we have some different ways that we can talk about the arcs of a circle. If we have a semicircle, that's going to be half of a circle, and that's going to always equal 180 degrees. We can have a minor arc. That's part of a circle that's less than 180 degrees, so it's less than half of a circle. We name it by its 2 vertices, a starting point and an ending point. So in the diagram over here on our right, we can see arc AB, and we can see that that's a minor arc because it's obviously less than half of the circle. The minor arc will be equal to the measure of the central angle. That's what I just said. Whatever this angle is right there, that's what the measure of the minor arc would also be. We could have a major arc. So a major arc is an arc that's greater than 180 degrees. So it's bigger than half of the circle, and you have to use 3 vertices. You have to have a starting, you have to have somewhere in the middle of it, and then you have to have the ending. So right here on our right, down near the bottom, is the major arc D, E, F. So I start at D and I go clockwise toward F. Now, real quick memory here. Clockwise is this way, all right? So you would start at 12 and you would go around like the clock of a hand. Counterclockwise would be you'd start here and you'd go backwards. So, little bit of terminology there for you. Now, if you know, remember that a circle has 360 degrees, and if you subtract that central angle, you'll get the measure of the major arc. So here's an example where we're going to identify the different arcs in this circle. So if we had to name a minor arc, we could name AD or we could name DC. They're both originally in pink. If we had to name a major arc, that would be the arc in green. It would be D, C, and then all the way around to A. We could also name that arc as D, A, C. Okay, so we could go backwards, counterclockwise, and also name that arc. Another thing, you could name these a couple of different ways. You could say A, C, D, that could be another major arc. So you won't always have one correct answer when you're trying to name these things. If we wanted to name a semicircle, well, that would be the one in orange right here, and that could be AC. The biggest thing is how you name them would depend on if it's the lower half of the circle, because if we named it CA, we might want to start here and go that way. So it kind of just depends on how you're looking at it as to what you're going to name it. So adjacent arcs are arcs on the same circle that have exactly one point in common. So this arc DC would be adjacent to arc CA. So they both have that common point, C. And then the arc addition postulate, it works just like the angle addition postulate did and the segment addition postulate worked. Do you remember what those were? We did them a long time ago. Basically, it says that if I have this image, if I add angle A, B, C, and we're going to call this D. If I add angle ABC to angle CBD, right? ABC, CBD, that would give me the big angle here, ABD. So if I add two of them together, it's going to give me a bigger one, is basically what we're saying. So if in this arc, if I have arc, I like using green, if I have arc AC, and I added it to arc CD, that would give me arc ACD. Okay, same idea. That's a little bit of common sense, I think. Okay, so you're going to have some examples of circle graphs. And example 4 says, the circle graph shows the types of grass planted in the yards of one neighborhood. I need to find KLF. So KLF is what I got to find. So KLF looks like it's 65% of the circle, right? That's this whole piece. So what we're going to do is, how many total degrees do we have in a circle? We have 360, I'm writing a percent. We have 360 degrees total in a circle. 65% of that.
Tanner Brooks, please call extension 506.
Well, yeah, I'm at school making a video, and sometimes when the announcements come on, you guys get to hear them too. So we have 360 degrees total in a circle. This grass is 65% of that 360 degrees. So when you're given some percents in a circle, that whatever percent is out of the 360. So we're just going to multiply that. The percents are a little weird, and you might see a couple of these problems from time to time. And oh my goodness, on the Desmos calculator, do we have a percent sign? And I did this without even explaining it. Remember, when we have percents, that's the same thing as moving the decimal 2 places, 0.65. So that's why I'm just going to type in 0.65. And that equals 234 degrees. So the measure of that arc is 234 degrees. Now, quite honestly, I don't know why you would want to talk about 240 degrees of an arc instead of a percent when you're talking about something like grass in a neighborhood. But that's how you do that problem. Here's another example. If we wanted to find the measure of angle FMC. FMC is the pop, the country, and the R&B, rhythm and blues. So we have 9% plus 10% plus 11%. How many percents would that be? I don't know. Let's add them and see. So we're adding 9 plus 10 plus 11. That equals 30%. So again, this arc would be 30% of 360 degrees. So 0.3 times 360 is 108 degrees. So this arc is 108 degrees. Now the problem asked for the angle. Remember, if this is a central angle, this angle and this arc are going to be the same. So the measure of angle FMC is 108 degrees. Fabulous. All right, the next problem, we want AHB. AHB. Wow, that is all the way around. The only part that I didn't include is this piece. So the AHB is other music plus jazz, classical, pop, country, rhythm and blues, all right? 1, 2, 3, 4, 5, 6. It's 6 of those things added together. Now, the only part that wasn't added was the rock part, and that was 25%. So again, I could add all of these things together and then multiply that by 360. Or another way to work this problem would be if I said 0.25 times 360 degrees. What's that going to give me? 0.25 times 360. That gives me 90 degrees. Okay, so this is 90 degrees right here. If I just said 360 subtract 90, the part I didn't include, that would give me all the other ones, right? Well, 360 subtract 90 is going to be 270. So the measure of arc AHB is going to be 270 degrees. Okay? Different way of looking at the same kind of problem. All right, so our arc addition postulate says if I add these arcs together, I'm just going to get the bigger one. So I want to find the measure of BD. All right? I want to find the measure of arc BD. Okay? Now, here's my first question. How do I know that I'm finding the blue side and not the green side? First of all, how do I know that? Well, I know that because this is how you would label a minor arc. Remember, minor arc, 2 letters. A major arc would be 3 letters. So if I were talking about the green one, I would have said B, can't even write, B, what in the world? Why is it doing that? B-A-D, or I would have called it B-E-D. Either of those arcs would have meant the green one. But since that's not what I have listed, I know that it's the smaller one. It's the minor arc. The reason I did not include the C, because if I had used 3 letters, I'm talking about a major arc. The blue one is obviously smaller than half of the circle, so I know it's a minor. All right. So what do I got here? Well, I don't know. Like, I don't know what this is. I don't know what that side is. I know what this is. And this is half of my circle. Wait a minute. How much is half of a circle? It's half of 360? 180 degrees. So if I said 180, subtract this 52, that would leave me with BC, right? Yeah, it would. So you got to think about how you got to look at what you have, and you got to see what you can do with those numbers that you're given. I only had this information. I had to know that this is a diameter. It's obvious that it's a diameter. And so I know a diameter is 180. I know that I've got this 52 and I've got this 97.4. This 97.4 isn't really very helpful. I mean, not really. So this is what I'm looking for. So I got to use that 52 somehow to figure it out. And the more you do these problems, the easier they're going to get. I need to find JKL. So JKL. All right, again, I'm looking for my diameter. It's 180. 180, subtract this 40 will leave me with what I'm left over with, which is going to be 140. That's pretty easy. That was just like the same one. LJ LJN. Now, here's the reason I paused for a moment. This is labeled bad. It should have just been JL. Okay? Because JKL is a minor arc, not a major arc, and it shouldn't have been labeled with 3. So, there we go. LJN. LJN. Wow. That's all of this right here. So what am I not using? I'm not using 40 and I'm not using 25. So this time, since I'm talking about the whole circle, I'm going to say 360, subtract 40, subtract 25. Because I'm talking about the bigger piece and not just half of it. So 295 degrees. So that arc measure is 295. Find the measure of the arc or central angle indicated. Assume that lines which appear to be diameters are actual diameters. All right, so this looks like a diameter, and this looks like a diameter. Okay, what kind of angles would these be? Do you remember? They're congruent. You're absolutely right. They are congruent angles. And their type is vertical angles. So vertical angles are congruent. And these are also central angles. So central angles are congruent with their arc measure. So basically, I'm going to be able to say that 9x plus 7 equals 11x minus 5. So 9x plus 7 equals 11x minus 5. What do we get here? X is 6. Is that my answer? No, I was trying to find HI. So if I'm trying to find HI, I need to substitute that 6 in. So 11 times 6 is 66, minus 5 should be, oh, I hit the wrong button. Minus 5 should be 61. So HI is 61 degrees. All right, what's going on here? So here's my diameter. FE is this piece. That's what I'm trying to find. So 7x minus 6 and FE are going to be the same thing. And then I have this. Well, if I wanted... if I added these two pieces together, it would equal 180. And I could write 7x minus 6 up here because these two things are congruent. So 7x minus 6 plus 16x plus 2 is going to equal 180. Why did I pick 180? Because that's the diameter. That's half of the circle. So you got to be able to tell when you're going to set it equal to something or when you're going to have to add it and set it equal to 180. Or sometimes maybe you have to add two things and subtract them from 360. I don't know. You've got to look at each problem. Each problem is going to be a little bit different, and you're going to have to figure out what you need to do. So let's erase some of this stuff now. I'm trying to find FE. So now I'm going to substitute. So I'm going to do 7 times 8, because you know I can't remember my multiplication when it comes to the 8s. And that's going to give me 50 degrees. If this is 50 degrees, what would this piece be? Super quick, do it in your head. 180 subtract 50. Right, that's 130. Good job. All right, we're going to pause there for a moment and we're going to stop our video just because these videos get too long and it's hard for them to upload.